So this simulation shows the connection between spring motion, that oscillating up and down, and rotational motion. You can see that here. What the simulation is plotting is just the y component of the oscillation, of the circular motion. So if you take the circular motion and only plot its y position, notice that the red ball goes up and down at the same rate that the spring does. And so you see this position versus time. The arrow is also showing you the velocity versus time. So in this case, the arrow again for this simulation is showing you the y velocity only, not the angular velocity or anything like that. So this y velocity that you see down here, this arrow, is the direction this is going. You could get it actually as a slope of this graph, right? Because velocity in the y direction is dy dt. And that's going to let us get to energy as we go along. Sorry, Vy equals dy dt. And so we're going to use that and look at both the energy of this, but I wanted you to see that this omega that we looked at, so we would describe this as y of t is equal to its amplitude. In this case, this is a cosine omega t, right? Where this time, again, that's our period, and omega equals 2 pi over the period. So what happens for this rotating object, right? It's rotating that way. The omega, which is into the screen in this case, is going to be just set up so that it's set spinning to match the omega for the spring. Okay, so that's your V. And what I want us to look at first, before we look at the energy, is to actually look at why a sine is actually the right equation for a spring. So we have Vy is equal to this. I'm sorry, y is equal to that. Vy, the y component of the velocity for the turntable, and sort of just the only component that we have for the mass on the spring, is of course dy dt. So if we take that derivative, we're looking at a times the derivative with respect to t, because a is a constant, we can pull it out, cosine of omega t. And so this is taking the derivative of cosine, and just to remind you how that goes, Vy is equal to a derivative with respect to t of cosine omega t. We're going to take the derivative of cosine, which gives us a minus sign, but then we've got to do a chain rule because we've got to take what it's a function of inside, because it's not just cosine x. We're not just doing d by dx cosine x. We're doing instead d by dx of something like cosine 2x. And you may, hopefully you remember, you take the derivative of the function and then you take the derivative of whatever it's a function of, if it's not exactly what you're taking the derivative of with respect to. So this becomes then a minus sine of omega t times the derivative with respect to t of the argument, right? Just omega t, and that derivative is just omega derivative of t with respect to t, which is just 1, right? T to the first power just gives us 1. So this all becomes Vy is equal to minus a omega sine of omega t. Okay, and just to finish this out, we're going to find the acceleration. This would be the acceleration of the mass on the spring, is derivative of velocity with respect to time, which becomes the derivative with respect to time of this whole thing, minus a omega sine omega t. The a and the omega are constant, so we can pull them out. I'll pull out the minus sign at the same time. D by dt sine omega t. Same thing I do here. Take the derivative of sine, so that gives me a omega cosine omega t, and then I've got to take the derivative of the inside, d by dt of omega t, And so that's going to give me minus a omega. Then I get another omega out of this derivative, so omega squared, whoops, cosine omega t. So that's my acceleration. So if we look at a spring, then for a spring we have F is equal to, or anything, we have the sum of the forces equals mass times acceleration. If we do a mass on a spring, we'll do it this way just to make life easier. So we don't have to worry about gravity to start with. Then we can say that the acceleration, this is all going to move in the x direction, so we'll have x is equal to a cosine omega t. Vx would then equal minus a omega sine omega t, and a, the acceleration, is equal to then minus a omega squared cosine omega t. If we put it into force equals mass times acceleration, and we only have the spring force acting on it, we get minus kx is equal to ma. And we can check that these expressions actually work, that our expression for x and getting our expression for x and a actually makes this work. And the way we know that it works is if the time falls out of this. So I put this in, I get minus k, I put in a cosine omega t is equal to m, then I'm going to put in my expression for the acceleration, minus a omega squared cosine omega t. So I hope you can see that I substitute that in here, that's this, and then I substituted this expression right in here, that became that, okay? And what this allows is to connect this omega to the spring constant. The first thing we notice is that the amplitude goes away. The amplitude just depends on how far you pull the spring down, and then this cosine omega t goes away, which is a way of saying, hey, this is a good solution to the problem, because all of a sudden these constants don't depend on time. And then I've got minus k equals minus m omega squared. The minus signs even work out, so that's nice. And we get that k is equal to m omega squared, or omega is equal to k omega squared is equal to k over m, and omega is equal to the square root of k over m. So if we set a spring oscillating, we let it oscillate back and forth, then its frequency of oscillation, this omega, how fast it's going to oscillate back and forth, depends on both k and m. And if you remember, omega is equal to 2 pi over the period, which we can also write as 2 pi times the frequency, where our frequency is measured in hertz, if you like. So as you have a bigger omega, you have a higher frequency. It goes back and forth more frequently. And so if you have a higher spring constant, that makes sense because it draws the mass back. And if you have a smaller mass, then that gives you a higher frequency as well, which makes sense because it's easier for the spring to rebound. So this omega, which we had talked about before as an angular velocity, is, here we would call it an angular frequency. It's really the same thing because it is radians per second. So you can call it an angular velocity or an angular frequency. For an oscillating mass, it doesn't, on a spring, it doesn't make sense to really talk about it as an angular measurement. But if we compare it to this, the oscillations that this has up and down are going to match the oscillations that match the angular speed, where the angular speed is given by this turntable. Finally, another system that exhibits simple harmonic oscillation is a pendulum, at least at small angles. And so you can see here in this simulation where the pendulum is going back and forth, and the motion at the right is a plot of energy, which we'll get to in the next video. But here I just want you to see that the motion of the pendulum can also be matched to the spring. What controls the oscillation of the pendulum is actually the length of the pendulum. It turns out not to depend on the mass the way it does for a spring, but the period of oscillation depends on the pendulum length, and that sets the frequency of oscillation.